Okay. We can generate the example about the calculation of the what this transform example. And so let's consider two-dimensional state vector. State vector x hat 1 and 2 with P covariance matrices 1, 0.5, 0.5, 2. Okay? And also we can select the n is equals to the what 2. Alpha may be equals to what 0.001 and kappa maybe 0 and beta is normally 2. Okay? And so how we can calculate all the parameters just like this one. So first of all, this is the solution. Then lambda alpha square times n plus kappa value minus n. Okay? And so 0.001 square times 2 plus 0 minus 2 is equals to 1, 9, 9, 9, 9, 8. Okay? After that, we need to compute the weights. Weights. So W0m lambda divided by n plus lambda is equals to minus 9999990. Okay? And so WIM is equals to the what? 1 plus 2 n plus lambda is equals to 25,000. Okay? And also we need to compute the V0C value, which is equals to V0m plus 1 minus alpha square and beta, which is equals to the what? Minus 99996. Okay? So after that, we need to compute to what? To S matrix, just like this one, but in the square root form, which is equals to the what? The S is equals to what? N plus lambda times P, which is equals to 0.00002 times P. Okay? And so this indicates that this value is too small, and this is the covariance matrix of our error matrix, and so this gives us numerically instability, because if we take to what the inverse values of these terms, this S, and so this gives us the numerically instability conditions. Okay? This could be the infinity values in here, just like this one. And so this matrix cannot be, cannot be to what? To be inverted by using this one, because it's closing to what? Is closing to zero matrix. Okay? So maybe we need to what? We need to select the alpha parameters to the what? To the greater in here. So if we learn everything about this one, how we can build the UKF algorithm in here. Steps. First of all, we need to begin with the prediction step. We have two steps in here, the prediction steps, and also we have the update states. First of all, we need to generate sigma points. Okay? And so, how we can do that? We can do this to use sigma points, which is chi k minus 1 previous value with the I in this from previous time steps. In the second place, we should propagate sigma points through process model. Okay? How we can do that? The chi k minus 1 I is equals to the what f x k minus I u k minus 1, which means that it's the nonlinear dynamics. We should assign in the first place this nonlinear dynamics into this one. Okay? This is the chi value. After that, we need to give the calculate the what the predicted state mean in here. Okay? But how we can do that? The x hat estimated k minus 1 value is equals to what? I equals 0 to n w e m mean and xk k minus 1 I. Okay, which means that we have this signal xk k minus 1 in the real-time application, and so this is equals to what? The upper bound is given by w e m, right? And so the lower bound is e plus n m. Okay, or the otherwise. And so we can generate what the state mean, and also we can bound these signals just like this one. And after that, we should calculate predicted state covariance. Which means that the p k minus 1 is equals to what? E equals 0 to up to what? To n. Because this is normally the n state values, but we need to give the 2 times n because we have the upper bound and the lower bound. And so WEC, the covariance, chi value k minus 1 I minus x estimated or the hat k minus 1 times chi k minus 1 I minus x hat k minus 1 transpose plus q k minus 1. Okay? This is are the state covariance matrices in here. And so we want to try to the what to this pkk minus 1 values into the what into the going to 0 or minimize these values in here. So for example, how we can build an examples in here for the nonlinear system. The prediction step is built with the what? The fxu value is equals to x1 plus u1 x2 square. This is non-linear u2, and uk minus 1 may be equals to what is 0.5 and 1.0, and qk minus 1 can be selected 0.1, 0, 0, 0.1. Okay, these are the selection matrices. And so the using sigma points chi k minus 1 I, then we can write it x k k minus no chi k k minus 1 I in this can be given by with the what the chi k minus 1 1 I plus u1, and so the other term chi k minus 1 2 is the x2 state in here I square form plus u2. Okay, these are the conditions, and so the chi can be built just like this one because it's the nonlinear dynamics, and so chi contains the what the R nonlinear dynamics, guys. Okay. In the MATLAB example, you can easily find out how we can define these values based on these terms. Okay, and so I will show you. So in the second place, the update step can be showing right now. First of all, in the one, the propagate sigma points for measurement model, just like this one. If this is the true, and so gamma k I value is equal to what? H chi k k minus 1 I can be written just like this one because the h can be nonlinear in here. Okay. So after that we need to calculate the predicted measurement mean. Okay, zk hat is equals to what? I 0 to 2n, and so we m weight times gamma k I. This is simple. And so in the third place we need to calculate innovation covariance. Okay, and so sk is equals to the what? I is equals to 0 to 2 times n wc wic gamma k I, and minus to what? Zk value, right? Because it's the what? The predicted measurement mean. And so this is the measured mean, right? And so gamma k I minus zk hat transpose plus rk can be used in here. Okay. And so how we can use this innovation covariance and the mean values? See that this is the what? This is the sigma point measurement model, and so zk is the predicted measurement mean. Okay, and so innovation covariance can be found just like this one, but this is entirely depends on what? The measurement and the what? The measurement mean, predicted values of it. And so we need to add one more data or conditions, which is called to the what? The calculate cross covariance. In normal Kalman filter, or in the extended Kalman filter, we don't have this kind of property, okay? And so P x is z is equals to the what? Summation operator I equals 0 to n wi c times chi k minus 1. See that? This is the nonlinear dynamics. Minus xk k minus 1 hat times. This is our the nonlinear dynamics. Nonlinear dynamics error. And also we need to give the what? Gamma k minus zk transpose. This is the observation. Nonlinear dynamics. We are a huge advantage using this cross covariance matrices because the normal Kalman filter or the extended Kalman filter does not have this kind of properties in here. And so if we want to deal with the nonlinear system, we need to compute the Kalman gain. Kalman gain, just like this one, kk is equals to the what? Pxz times xk minus. Okay? Because we need to deal with to the what? First, innovation covariance, the observational or the measurement covariance matrices and the cross covariance matrices must be computed based on these informations. Okay? Because in the inverse values of this is the transform values and this is the what? This is the nonlinear dynamics and observational dynamics are crossed over to each other, and so this innovation covariance threat to the what? To the measurement error. Okay? And so after that we need to return to the normal Kalman filter, just like this one, the update estimation, which we can use the what? The xk right now hat is equals to the xk k minus 1. It's the previous observations. Okay? K minus 1 plus k times zk minus zk hat. Okay? The zk is the real measurement. With the noise. With noise. This is the real measurement with noise. Okay? And also we need to what? We need to update covariance estimate. Which means that we can do this to the what? The pk forward value, pay k minus 1, it's the previous value minus k times sk k transpose. Okay? And so this is what? This is the progression of the pk matrix in here. And so this is the update estimate matrix in here. And so computing Kalman gain based on this information. And so the other terms is given the different line. And also we have the innovation covariance in here, just like this one, and predicted measurement, and also sigma point measurement. Just remember that this chi value includes the nonlinear dynamics, and so this nonlinear dynamics can be used in the what? In the unscented Kalman filter, in the what? In the cross covariance form of these terms. Okay? And so this cross covariance form of these terms, the nonlinear dynamics matched with the what? With the estimated one in here, and as well as the observational nonlinear dynamics. Okay? So this is how we can predict, just like this one, this one at the fourth stage, and the update of the unscented Kalman filter. In the next lesson, we will build to the what? To the MATLAB script example sessions about the what? About the Van der Pol equation and the DC motor dynamics. Okay?